Hello everyone, my name is Vipra Joshi and I am an assistant professor at St. Andrews Institute of Technology and Management in Electrical Engineering Department. Today I am going to deliver a lecture on subject of basic electrical engineering. In this video I will be explaining Thevenin's theorem. This is Unit 1 topic of second semester. In this video, we will be see what is Thevenin's theorem in the electrical circuit. So, in previous video, we had to see different technique like KVL, KCL, and we had to see that using these technique how we can reduce the circuit and find the voltage and current any element in the circuit. Many times in electrical circuit it may be happen that a lot of many circuit elements are given. So more number of resistance and voltage and current source. And we are supposed to find out what is current and what is voltage across the particular branch given in the circuit. So at that time it is better if we reduce that circuit into a simple one by using basic law which we called Ohm's law can be applied to get the whatever they have asked, either is current or voltage. So here we are going to learn a new technique called Thevenin's theorem. Thevenin's theorem states that any linear circuit containing several voltage and resistance source can be replaced by just a single voltage in series and with the single resistor. We can see here the overall voltage is represented by this, and this total circuit resistance, we can say Thevenin's resistance is here and load resistance is here. So we combine the Thevenin's voltage and Thevenin's resistance with the load resistance in series. This is Thevenin's theorem. So it is possible to simplify any complex linear circuit to an equivalent circuit. This is equivalent circuit. Okay. So how we can make equivalent circuit? We just apply a equivalent circuit with just a single voltage source and series resistance connected to the load, where voltage is called Thevenin's voltage, this voltage is called Thevenin's voltage, and which is obtained between the terminal where load is connected after removing load and a voltage. And this resistance is called Thevenin's resistance, which is obtained by same terminal after removing load and replacing all the power source with their internal resistance. So a lot of many things are involved in this particular theorem. Let's see one by one. Thevenin's theorem requires the following step. First, find the Thevenin's resistance by removing all the voltage source and the load resistance. Second is find the Thevenin's voltage after it. And third is use the Thevenin's resistance and voltage to find the current flowing through the load. So, important concept it what is meaning of Thevenin's voltage and how it is obtained. And second is what is Thevenin's resistance and again how we can get it. In order to understand, let's take a numerical. This is a circuit. We calculate this circuit by the Thevenin's theorem in the load of AB. Here load is AB terminal. It means the load resistance here is 40 ohm. So the first term is we find the Thevenin's resistance. We first need to remove the 14 ohm load because the first step is removing the load resistance. We know that here the load resistance are connected the terminal A, B. During this, we will provide us with the open circuit at 0 volt, which leaves just a 2 resistor wire in series. If we see here, after removing the load resistance, it seems like a open circuit. Okay, then we can see that these two resistors are in series. But to calculate Thevenin's resistance, we can use formula for the resistance. If we see here, we can see that in this like that these resistance are in series, but here if there are terminal A and B, we can see that the both resistance are in parallel. So apply parallel resistance formula to solve this circuit. We know that R1 into R2 upon R1 plus R2. So if we calculate resistance, we can find here the value of resistance is 6.67 ohm because R1 is 20 ohm, we put here, and R2 is 10 ohm, and R1 plus R2 is 20 plus 30 equal to 10 equal to 30 ohm. So the value of Thevenin resistance is 6.67 ohm. Now we find the current flowing through the branch. For this, we can apply Ohm's law. Here, the I current flowing through the branch, okay, and the voltage is 20 volt and 10 volt. So we know that I is equal to V over R. Here, these resistance are in series, and V is difference between these two voltage. So if we calculate here current I, we know that I is equal to V upon R, and here two voltages are 20 volt and 10 volt. So 20 minus 10 upon 2 resistance in series, 20 plus 10, it means 30 ohm. So if we calculate this, we find here the current flowing through the branch is 0.33 ampere. Since these two resistors are wired in series, they will share the same amount of current, 0.33 ampere. We can use these resistor value and our current to calculate the voltage drop across the terminal AB. Means we calculate the voltage drop across this terminal and this terminal. So at first we assign polarity for resistance. If we assign, here is positive, negative and positive, negative. So if we find voltage drop across VAB terminal here, so here is voltage is 20 volt, so V minus I into R. V is 20 volt minus, here the sign is negative, so minus I 0.33 ampere into R is 20 ohm, like this equation. So 20 minus 20 ohm, this is R, and current, this is voltage. So V minus I into R equal to 13.33 volt ampere. And same, if we apply this formula for this terminal A, and we have to calculate VAB voltage. Here the source voltage is 10 volt, so we assign polarity positive, negative. So here is, if we take this terminal, then 10 plus 10 into current is 0.33 ampere. So the second equation become it. 10 plus 10 ohm into 0.33 ampere equal to 13.33 volt. So these are the voltage at terminal VAB by the resistance 20 volt and by the resistance of 10 volt. Now the third step is to find the load current. We know that by Thevenin's theorem, if we take this circuit in the equivalent circuit, we combine the Thevenin voltage with the series in Thevenin's resistance, and these two voltage and current are connected in series with the load. So here both resistance, Thevenin resistance and load resistance, look like in series combination. Now if we find the current, we know that V is equal to I into R and I equal to V over R. So here the Thevenin's voltage is 13.33 volt and the Thevenin's resistance is 6.67 ohm and the load resistance is 40 ohm, which is given. So by this the load current is, if we calculate, the load current is 0.286 ampere. So this is the equivalent circuit of Thevenin theorem. In this circuit the total load current is 0.286 ampere. Now here we will discuss the second example. Refer to the circuit below. Find I3 in the following branch. Here the current I3 is following 15 ohm resistance branch. If we see here at this node, I1 is incoming for this node and I2 is outgoing for this node and I3 is also outgoing for this node. But we calculate this circuit by the Thevenin theorem. So at first we know that the first step is remove the load resistance. So if we remove this load resistance, our circuit like this. In this first step, our circuit like this. Here this load resistance like a open circuit. So the all current produced by this source is flowing through the both resistance. Here we can see that these two resistance are in series. So the second step is we find the Thevenin voltage. So here we can apply, means we can find Thevenin's voltage by any method. So here we can apply voltage divider rule. We know that voltage divider rule is applied for the series circuit. So if we want to apply voltage across this terminal 2 ohm resistance, we find, so here we know that the resistance R at which we find the voltage into the source voltage is 20 volt. So the formula is main source voltage into resistance at which we find the voltage upon the resistance at which find the voltage plus in series with the other resistance. So we apply, if this formula, we here the both resistance are 10 ohm and 20 ohm. So if we put these value here, then the Thevenin's voltage will come 13.33 volt. So the Thevenin's voltage of for this circuit is 13.33 volt. Now the third step is find the Thevenin resistance. We know that to find the Thevenin's resistance, we can apply the rule that both voltage and current source are replaced by their internal impedance. So here is only a voltage source, so we can short circuit it. After that our circuit became like this. So here we can see that both resistance are in parallel. Okay, so we know that in parallel the resistance R1 into R2 over R1 plus R2. So by this we calculate the parallel resistance. This is 6.67 ohm. So this is called the Thevenin resistance. Now in the fourth step we find the load current and Thevenin's current. So if we combine this diagram in the Thevenin's equivalent circuit, here the Thevenin's voltage is 13.33 volt and Thevenin resistance is 6.67 ohm and the load resistance is 15 ohm. So we know that V is equal to I into R. So I equal to V over R. Here the voltage VTH is 13.33 upon R. R is series with RTH. Load resistance is series with RTH, means Thevenin's resistance. So if we calculate this, VTH upon RTH plus RL. Here the value is VTS is 13.33 upon RTS is 6.67 plus RL is 15. If we calculate these value, we find the current is 0.615 ampere. This is load current or Thevenin's current for this circuit. By the Thevenin's theorem, we can simplify the complex circuit into an one equivalent circuit, and we can find the Thevenin current or load current by the voltage source or current source. Thank you.